we left off on example 6. So we're ready for example 7 now, where we actually have a picture drawn. And we're going to use the graph to solve the following inequalities. So we do not need a sign chart. We just need to look at the picture. So, what do you think? Where are we less than or equal to 0 in that picture? What are your thoughts on that? You're not even on the right page. So we are still in 1.8, example 7. We're looking at the picture and solving this inequality using the picture. So we would need to see where the picture is, touching the x-axis or below it, right? So which x values is that? Left to right, starting where? -3. Not included because that is an asymptote, right? Stopping where? -1. That is included. So my first piece of the answer is this. All right, is there any other places, are there any other places where we are touching the x-axis or below it? 2 to 3. And again, 2 can be included, but 3 cannot because 3 is an asymptote. Those are cannot be's, we don't touch those. Is that okay with everyone? How about bigger than 0? Where is it bigger than 0? That would be above the x-axis. Where does it start? -infinity. Very good, William. It goes all the way to -3. And then it picks up again at -1. Oops. -1 to 2. And then it picks up again at 3. And goes to, yep. Is that all right with everybody? How about greater than or equal to 1? You've got a horizontal asymptote at 1. So we want to know where are we bigger than, higher than that. So wouldn't that be -infinity to -3? Or 3 to infinity.
Do asymptotes always have a parenthesis?
Oh yes. Oh yes. Vertical asymptotes are cannot be's. So no matter what else happens, that is. Now, one problem I wanted to touch base on before we move into the next section. It's covered in the next section, but I want to make sure we talk about it in terms of the graphing that we were doing yesterday. So remember yesterday, we had a rational function like this, and we needed to solve it using a sign chart. So we're going to put it on a number line and figure out, where to shade. So what was the first thing we did yesterday? We didn't have one exactly like this, but we had one where we had to start by factoring. So we're going to factor it. Now, look what happens when I factor this. remember yesterday, all of these points were important points, and we put them on the number line. And then we figured out where we shaded and all that stuff. Well, these cancel. So our problem is really just this. But when I solve it, I still must include a dot at 3. Because even though that's what we call a removable discontinuity, or a hole, even though we have a hole there, and it's canceled from the problem, that 3 is still significant. Because in the original problem, I couldn't put 3 in. 3 is a cannot be. Not an asymptote cannot be, it's a hole cannot be. So I would have holes, I would have dots at 3, at -1, and at 4. And let's say, I can write this, let's say this is greater than or equal to 0. That dot would not be open. That dot would not be open, but this one could be open. Or closed, I mean. These would be open, that would be closed. Okay, and then we would proceed as usual, but that has to be part of your answer. Or at least a consideration on the way to the answer. Even if the factor cancels out, it still has to show up on the number line as an open dot. Okay? All right, we're going to spend more time with holes today, so let's look at next note. 1.8 will be due on Friday. Here we go. We already know we've got all this. Okay. A hole occurs when the factor in the denominator cancels out with the factors in the numerator. That's what we just talked about. We have to be careful with that though. So let's look at his examples here. Someone's already done the factoring for us. And we notice in both of these first examples, in that first column, we can cancel these out. So we are going to have a hole where x is 1. If I were drawing this on a number line, if I were solving an inequality or something, and we did on a number line, I would have an open dot at 1. I'm going to be graphing that in the coordinate plane. I'm going to have an open point somewhere in here where x is 1. There's going to be an open dot in the picture. Any idea how to find where that is? Plug in 1 right here. So that hole is going to be at 1,3. Now, this one looks a lot scarier, but it's exactly the same thing. Because won't 2 of these cancel with 2 of those? So we have left x minus 1 over 2. We're going to have a hole, and it's going to be where x is 1, because that's the factor that canceled out. This time, when I plug in 1, I'm going to get 0. Which is fine. So that hole would be like right here. Now, what's different about the second column? Because it looks very, very similar. What do you think? Does this one have any holes? No, because absolutely nothing canceled. However, this does have a problem at 1, but it's an irremovable, I don't know if that's a word. I can't get rid of this problem, so it's going to be a vertical asymptote. This is going to be a vertical asymptote. And x is 1. All right, look at the next one. This is the one that kind of catches us sometimes. I can cancel. But look what I'm left with. When I cancel, I'm kind of programmed to say, oh, I'm gonna have a hole. The hole would be at 1. But what happens? Can I plug 1 in? No, because I still have an x minus 1 in the denominator. So even though I cancel, this problem has no holes. It has a vertical asymptote at x equals 1. Okay? All right. Now, we need to talk about our vocabulary for a minute. So let's go back to this problem. Let's look at the first column. And it had a hole at 1. 1,3. And somebody scratched it. And it looks like this. Alright. Now, there are 6 limits in that problem that you need to be comfortable with. The 6 limits you need to be comfortable with are the limit as x approaches infinity. We'll call this f(x). The limit as x approaches negative infinity. Right, now wait a minute. Those 2 are old news. That's end behavior. End behavior is horizontal asymptotes. So what's happening as we go to the right? We're getting closer to 1 from the top. How about as we're going to the left? Getting closer to 1 from the bottom, from underneath. Old news. Now you also have to be comfortable with the limits as you're approaching your vertical asymptote. So as we are approaching -1 from the left and -1 from the right, what is happening to my curve? So here's -1. These are my end behaviors. That's my horizontal asymptote. These are what's happening around my vertical asymptotes. So what happens as I approach -1, as I come in towards -1 from the left side? What's happening to my curve? Negative infinity. That tells me that on the left side of my picture, I'm going down at the asymptote, the left side of the asymptote. I'm going down. What happens on the other side? Going up. So you need to be able to describe, using limits, what's happening on each side of the vertical asymptote. Then, you also have to be able to describe what is happening at the removal discontinuity or the hole. So what's the limit as x approaches 1 from the left and as x approaches 1 from the right? Here's 1. I'm coming at it from the left. What happens to my y values as I get closer to that point right there? What are my y values doing? What?
Decreasing?
Yeah, but not infinitely decreasing. They're decreasing toward what? 3. So that's 3. And what is the limit as I approach that from the other side. Also 3. Okay? So we need to be able to practice more. We need to be able to describe using the limits the end behavior of the function. You're good at that. And the behavior around the vertical asymptote and around the removable discontinuity. Okay. All right, let's look at the next page. Here we go. For example 1, for each function below, find the x values for any holes and or vertical asymptotes. All right, take a second on your own with your partner. See if you can come up with the holes and the vertical asymptotes for example 1. All you need is the x values. All right, friends, what you come up with? Does A have any holes or vertical asymptotes? Actually, both. We have a hole where x equals -3, and we have a vertical asymptote where x equals 5. All right, how about B? What do you think? Vertical asymptote where? At x equals -1. Yep. Are there any holes? There sure are. Where x equals 2. What about G? No holes. But there's a vertical asymptote at x equals 0. Very good. Now, hopefully, being stellar students that you are, you factored that denominator. And you took out an x. That's why we have the 0. But then you were left with x squared plus 4. That is solvable, but not over the real numbers. So that part I don't need to worry about in terms of discontinuities. So there's only one vertical asymptote and it's at x equals 0. Yes, Celeste?
For B, would there be two vertical asymptotes?
Would there be what?
Two vertical asymptotes?
No.
Or
Be-
why would two be on hold then?
Okay, because remember, vertical asymptotes are cannot be's. So if I look at my original problem, and I marked mine up, so I can, is that 2?
Yeah.
And then this was also a 2. Okay, so first thing I'm gonna do, this is alarming, discontinuities, but first thing I'm gonna do is see if I can simplify it all. So that can cancel out, leaving me with one of those. That can cancel out, leaving me with one of those. So my new problem is this. That's what I'm gonna graph. Now, x still can't be -1. So I'm gonna have a vertical asymptote and -1. In the original, x couldn't be 2, but now it can be 2. And in fact, when it is 2, this time I happen to get 0. But since it couldn't be 2 in the original, I have to make that dot and open dot. That's a hole. So if you can cancel something out and then plug it back in at some point, it's a hole. If you cancel it out and you can't plug it back in, I can't plug -1. That's impossible. So that remains a vertical asymptote.
So you give them 0 in the numerator,
Oh, absolutely.
but not the denominator.
Yeah, absolutely. Ever. Ever. Zeros on top of fine. Right? As Hollis always says, you can't sit on the egg. So no zeros in the bottom, but the top is fine. Okay? Everybody else okay with that section? All right, now example 2, you're gonna get a little practice writing your left and right hand limits as x approaches 2. So let's look at the first one. Doesn't even cancel in that problem. No. So therefore, won't I have a vertical asymptote at 2? Now, we haven't started graphing ourselves very much of this, but remember, this breaks your picture. Everything stops here. So as I come in from the left side, I don't know what kind of stuff's going on, but as I come in, I can't touch that. So what am I gonna have to do? I'm either gonna have to turn and go up, or I'm gonna have to turn and go down. So the limit at a vertical asymptote will always be a positive infinity or negative infinity. So your job is to figure out, okay, as I come in from the left, approach 2 from the left, am I gonna be going up, or am I gonna be going down? All right, so you're gonna figure that out, and that's gonna be the answer to the question, either positive infinity or negative infinity. Then you're gonna figure out what's happening as you come in from the right, positive infinity or negative infinity. All right, so take a few minutes and work on A, B, and C here, and see if you can find your limit statements as x approaches 2. I'm hearing some consternation, and I think talking it out is great, But boys and girls, let's not overcomplicate things. I am trying to figure out whether I'm gonna be going up or down here. So what could I do to really easily make that distinction? Plug in, oh, maybe 1. You can't plug in 2, don't plug in 2. But could you plug in 1 and 0? And if 0's up here and 1's down here, then it's going down. If 1's up here and 0's down here, then it's going up. Just plot a couple points and see what happens. This one's gonna have a slant asymptote. You don't have to figure that out yet. So I'd plot a couple points if I were you.
Oh, yeah.
would everybody agree that in problem 1, you're examining behavior on each side of the asymptote, vertical asymptote. And behavior at the vertical asymptote is always going to be going up or going down. Those are your only choices for vertical asymptote. So what did you come up with? What did you decide? From the left side, did you say positive or negative infinity? Positive infinity over here. And then was this one negative? It doesn't have to be, but it often is. What did you get on this side? Okay. This deafening silence is becoming a little irritating. Get your calculator out, graph this picture. This will be a no calculator question. You have got to be able to figure this out. It is not hard. You plug in points and you examine the outputs. Alright, we don't have more time to devote to this. So type it in on the calculator, look at it, tell me what happens. You're going to see a vertical asymptote. If you don't see everything you need to see, make your window a little bit bigger. Now, your calculator did nothing that you are not capable of doing. This is positive 2. If you plotted a point at positive 1, you would have gotten 0. And then if you would have plotted a point at negative 1, you would have gotten 4/3, which is higher than 0, which means that thing is going down. So from the left, it's actually negative infinity. Now, you have to be careful when you're plotting points. You want to stay close to the asymptote. You don't want to be coming clear out here and plotting points clear out here, because we want to know what is happening right here. Right here. And then on the right side, if you would have plugged in 3 and 4, you would have seen it coming down, which means as it goes this way, it is going up. Alright? So let's not be lazy and let's not be chickens. Let's jump in and do it. Alright, what did you decide about the second one? Now this one is different, because why? There's no vertical asymptote at 2. What is there at 2? A hole. And where is that hole? 2 comma what? Negative 6. So if I graph this, I'd have a hole down here at 2, negative 6. Now remember, I don't know what this looks like. It doesn't matter to me. I know that that hole is part of the picture. And since the hole is part of the picture, part of the actual curve, it doesn't matter which side I come at it from. My y value is going to be -6. It's not an asymptote, it's a dot. And you're gonna connect, you're gonna go through that dot. So when you come to it, that's the limit right there. That y value is the limit.
So is there not an asymptote at 3? Or,
Oh, there can be an asymptote at 3, absolutely, but that has nothing to do with what's happening in the
so
hole.
if there's a hole, you just focus on the hole?
Absolutely, you focus on the hole.
That was my question. I was wondering why we weren't focusing on the asymptote.
Okay, let's read the directions. Write the limit statements as x approaches 2. Not as x approaches 3, or as x approaches the asymptote, it's what happens at 2. In this case, it's a hole, and the y coordinate's -6. All right. What about C? Did you get anything for C? Is there an asymptote or a hole at C, or for problem C? At 2, we're actually gonna have an asymptote, aren't we? We're at an asymptote. So what does that mean about these answers? If I'm stranded on an island, I have no idea. It's gonna be plus infinity and minus infinity, right? That's gonna be my guess. Because if I'm a vertical asymptote, that's what's happening. I'm going up or down. All right, so can you figure out which it is? Take a second, figure it out. Do it without a picture, then graph it on your calculator and see if your picture, if your guess matches the picture. See if you can figure it out. Then use your calculator to verify. Or your neighbor, if you trust your neighbor to verify. What did you come up with? On the left side, did you say up or down? Positive up. And on the right side, also up? Or I think so, I got down. I didn't correct. I want to talk about this one now for a second. This problem was made a little bit easier because you have an asymptote at 1 and 2. Now, this is the only one I care about in the problem, but I have these close together, and I know the only place I cross the axis is out here at 4. So therefore, whatever is going on between these asymptotes, it's either all happening up here, or it's all happening down here, because I can't cross in between. Would you agree with that? This is the only place I can cross. Crossing is a 0, and a 0 will show up in the numerator. So therefore, I know whatever's happening in there, it either looks like this, or it looks like this, right? That's it. Can't look like anything else, because it can't cross. So I plotted 1 point, I said 1.5. What happens when I put in 1.5? Well, I get a negative over a negative over a positive. Well, negative over negative positive gives me a positive. So this is the version of the picture I want, and therefore on the left side, I have to be going up. Right? Now, over here, I'm kind of going to use the same logic. I cross right here. That is the only place. So therefore, when I put in 3, I'm either going to have a point up here or I'm going to have a point down here. Would you agree with that? So I put in 3. See what happens. Well, 3 would give me a negative over a positive positive. So when I put in 3, I get a number down here. These have to be connected, so therefore it is going down. Alright? Our brains are always working. Now, they're really going to work. Take a look at example 3. He gives us some limit statements. And then based on those, you're going to write an equation. All right, here we go. You and your partner talk this with A. Do A first, and we'll talk about that. Go to B. If we have time. Recognize when you saw these two that we must have a goal at 3, 5, which means that whatever your equation looked like, it's got to have an x minus 3 over x minus 3 because that's how I'm going to get a whole, right? And then when you look at these other two, hopefully you recognize you had a vertical asymptote at what? So this is a beginning of an equation. Would you agree with that? All right. why isn't this necessarily the answer, though, Charlie?
Because on the whole, when you plug in 3, you should get a 5 as the answer.
Exactly, so we know we're gonna cancel this. And then with what I have here, this is what I'd be left with, and if I put in 5, or 3, I mean, I don't get 5. Alright, so what did you do, you guys work on fixing that?
Yeah.
What did you do?
X plus 7 on the top.
Oh, you added another factor to the top. That's fine, there's no restriction on that. And now I would be left with this. And if I put in 3, do I get 5? Yep. Now, could there be other possible ways of handling that? Yes, but that is a fine example. Okay? All right, let's start working on the next one. It's the same thing. We're about out of time. Anybody come up with anything yet? What were the bones of it? What did you start with at the very beginning? What did you know? You know that you have a hole at -2, so you had to have that. And then it looks like we have a vertical asymptote at have an X plus 1 down here. So that's the beginning. So if I just cancel, I'm gonna be left with this now. We're gonna spend a little more time with this one, because this one's a little tricky. If you notice that the end behavior for the asymptotes is the same on both sides, that means when you plug in a number over here, this is your asymptote, you plug in a number over here, these guys are positive and these guys are positive on both sides. Wonder how we'll fix that, William? Oh, William says maybe I need to square something in here. Okay, start. We'll fix this up tomorrow sometime. And spend more time on it.
You don't have to watch it.
See if we can figure that out. If you can't sleep tonight, get it out. See if you can